Hi everyone, welcome to the first video of 5 where we're going to look at some basic transistor circuitry. Going to go through the math, see how these things work, see how to set them up. This is going to be within the context of a guitar pedal. We're going to look at how to set up a 2N3904 transistor, fairly standard part, should be easy to find. Parts wise, I'm going to link the parts used in the video and also some places you can get them. The idea of today's video is we're just going to go through how to set up a basic amplifier circuit so that we can get our guitar signal or any AC signal to be a bit bigger on the output. On the screen you can see what we're going to build today. If you've never seen a schematic before, that's okay. I'm going to step through how this works and what all the symbols and relationships are. This schematic will be linked in the description so you can get access to it. It'll be left up after the video, along with a list of bits and pieces that you might find useful, resistor color codes, capacitor reference sheets, the data sheet for the transistor, stuff like that. So looking at the input side on the far left, we have this pull down resistor, this 1 million ohm resistor, and this 100 nanofarad capacitor. We don't really need to know what the units are here, but all you need to know really is resistance is in ohms and capacitance is in divisions of a farad. It's named after the two scientists in the 20th century that discovered these units mathematically. But the first thing we want to look at is this little equation at the top here that says input and output blocks. This is going to let us work out what the frequency that we're letting through and the frequency that we're cutting out is. This applies to C1 and RPD1 and also C2 and RPD2. And as you can see here, we've got 1 over 2 times pi times a resistor times a capacitor. You don't need to know what pi is, just need to know that it's a button on your calculator. So if we do that math, we end up with 1.6 Hertz, which is very, very low, which means that essentially all of our signal is going to come through, which is good. If we move on to this RB1 and RB2 resistor pair, we can see that we have 9 volts DC. This is the same as what comes out of a battery or your pedal power supply. And this is the first kind of gotcha that you want to look for. DC power has no frequency. It's essentially 0 Hertz. So when you compare that to our guitar input, which is a AC signal or audio signal, which does have a frequency, we can see where this 1.6 Hertz is quite a nice number, because it'll stop the 0 Hertz coming through, but it will let all of our guitar signal above 1.6 Hertz pass. So this is doing, like I said, a couple of little jobs. It's going to be setting a minimum frequency that the circuit will respond to, and by doing that it will stop any of the power coming back into your guitar, or for that matter coming out of the circuit into your amplifier or the next stage. We will see how this works later on when we pull the circuit up on the breadboard. So the other little equation we've got at the top here is this base biasing block, which is a relationship that tells you how much of this input voltage here, this 9 volts, is going to make it through to this point at pin 2 on the transistor. So if we do the math, we take RB2, which is this 68K seen here, and we divide it by the sum of both of them, and then times the 9 volt by that result, and we get 2.135 volts. I've gone into 3 decimal places because when we get down to other stages, they come into effect. But all you need to know really is anywhere from 2 to 2.1 on your circuit, if you're building along, is perfect. That's where you want to be. So once we've got this number here, we can now start working out what happens on the output side of the transistor, and also on the think of this as the gain, setting the gain of the transistor, and how we can balance these two in relation to this this input on the pin 2. So the first little question you might ask is, why pick 2.1 or any voltage at this point? The easiest way to think about it is we want headroom on the output, so we want as much positive, think about an AC signal where you've got a positive section and a negative section, and it moves around a midpoint repeatedly. So we want equal space between 0 and 9 volts for it to move up and for it to move down. And the way we do this is we pick a voltage at the input that will end up setting our midpoint at around, or as close as you can get to, 4.5 volts, or whatever your input voltage is divided by 2, the mid point of your power. So it works out with this circuit, if we use 2.1 volts at pin 2, the math at the top here, the math at the bottom here will explain the math at the top. So this, generally transistors lose about half a volt from pin 2 to pin 1. So when you're measuring this, you'll see 2.1 on pin 2, and you'll see around 1.4, 1.5 volts on pin 1. The reason this happens is kind of like, if you think about a stiff tap in your kitchen or something, you've got a flow of water coming down from the 9 volts to pin 3, that's your mains feed. And then you've got the sink plug, which is flowing down. It wants to flow down through the tap to the plug hole, and you've got a stiff tap on pin 2. So you need to put, it doesn't just open immediately, you have to put a bit of effort in to get it to start to turn. That's this 0.65, it needs a little bit of a push to start opening, and then the water can flow through the tap to the sink. So if we put 2.1 in, we lose a little bit of effort, and we end up with 1.4 volts here. The way this 1.4 volts works with the resistor is through Ohm's law, where we use I for current, but you can think of current here, which is the amount of water flowing through the resistor, is the voltage, this 1.4, divided by whatever the resistance is. Which, if you think about it logically, makes sense, right? If you've got a thinner pipe here, you end up with more pressure, but actually less water's flowing through. If you have a thicker pipe here, or a wider pipe here, the pressure drops, but actually more water flows through it, in terms of path of least resistance type logic. So if we do that math really quickly at the bottom here, you can see that we end up with approximately 0.45 milliamps. Again, don't worry about what these units are in the video. Just know that when you're measuring this stuff at home, if you see these numbers in your circuit or something close to these numbers, you're doing good. I will probably link a bit of reading material explaining more about why the units are in their relationships, but for this video just look at the numbers and understand how they are, how they relate to each other. So just to recap how we go from pin 2 and how that relates to what we see on pin 1, we have a signal that comes in which has information above 1.6 Hertz in it, and we have power coming down which is 0 Hertz but with 9 volts. So we have whatever our signal is coming in, let's say our guitar signal, and we have some power coming in. The power is contained in this middle section, which is what we want because we don't want it blowing up our guitar or blowing up our amplifier. And then we have this division here that happens, which essentially means that our guitar input signal gets added to the 2.1 volts that results at this pin 2. And then we lose some of that 2.1 volts coming in here, and we end up with 1.5, let's say, volts at this point. That then gives us a 0.45 milliamps, you know, a little trickle of water that's coming through to the sink. So this is like if you didn't quite manage to turn off the tap properly and you just had that drip going to the sink. So the rest of the signal has to go somewhere, right? So it tries to go back up into the mains pipe, which is going to be where our output comes from. This is like putting a hole in your mains, mains pipe in the street. You'd get a big, fountain of water coming out, right? So this math at the top here, this collector resistor, which is pin 3, we have this curious thing where the collector current is equal to the emitter current, which again, if you think about it, makes sense, because if you have the tap wide open, then there's no resistance, so the water flowing from the mains pipe through the sink plug is the same, right? So we have 0.45 milliamps at the bottom, and we have 0.45 milliamps at the top going through this resistor and this resistor. So these two pipes are the same thickness, the same width. So we've got the same pressure and the same amount of water flowing through this section. So that's quite handy because now we can work out what the voltage is here, because we know what the voltage going in is, and we know what the amount of electricity flowing through is, or the pressure at the top here and the amount of water flowing through. So we can do a really simple sum here. To work out the voltage across this resistor, we can take our 0.45 and multiply it by 10,000, which gives us, when we do this math, it gives us a value of 4.5 volts. Right? Which kind of makes sense, because if we want this to have symmetric positive up to 9 and symmetric negative down to 0, to have our sine wave not squared off or distorted at all, then we want this point here to be plus 4.5, so that then we can go down negative 4.5 to 0 and up plus 4.5 to 9. So this target that we're looking for on this node here between the 10k and the 100 nanofarad wants to be whatever your power is divided by 2. So by setting the base up with this voltage, it means that we end up with 1.5 volts on the emitter, which means that the tap is on, but only enough to let the pressure at the mains be halved from what it would be if the tap was off, which means that if you put a hole in the mains, the height of that fountain that would ping out of the street is only half as high as it would be if the tap was off. I don't know if that analogy helps a lot, but that's the way I think about it anyway. And then we've got another capacitor with a resistor, which just makes sure that whatever happened in the middle here in this amplifier, we still end up with everything above 1.6 Hertz and nothing below it, which means that all of this power here stays on the right hand side of this input capacitor and the left hand side of this output capacitor. So anything we plug our amplifier into is going to be safe, and anything we plug into our amplifier is going to be safe, which is great. But how do we work out how much extra volume we're getting? Well, there's another really simple little relationship where there's two ways to work this out really. If you happen to have this system built already, you can simply measure the output voltage and measure the input voltage and then divide the two. But if you don't have this system built already, or you're designing your own, it works out that you can take your collector resistor, this 10K, and you can divide it by the emitter resistor, this 3.3K. K being 1,000 here, I should have mentioned that. So you've got 10,000 divided by 3,300, which gives you a gain of approximately 3. Now that's a voltage multiplier, so if you put 1 volt in, you would get 3 volts out, which is fine for if you're working in electronics, but what is that in terms of sound? Well, if you put 1 decibel in, it turns out that with the decibel system, you would get approximately 9.5 decibels out. I've done a little bit of pre-working out, and we can look at some things that we can measure on the breadboard in a minute. So this will serve as a recipe for anyone building at home, as well as the schematic. And it'll also work as a check sheet, so when you're looking at your circuit with a meter, or your you want a benchmark to work against, this is the bit you want to screenshot. So in a lot of schematics you'll see transistors as opposed to op amps, which are another amplifier chip labeled as Q1 or Q2. If you've got multiple transistors, there'll be Q1, 2, 3, etc. The part that we're using, and you can Google this and you can find the data sheet, I'll link one in the description, is called a 2N3904. So that's the part that we're going to be using. I'll link a little kit on Amazon that includes all of these parts, so you can just color by numbers and follow along. They have a value associated on the data sheet called HFE. This is essentially this is like on a guitar amplifier you might see like the wattage of it, like 100 watts or 25 watts. It doesn't mean that it's always at that volume, it's just what it can do. So I've just used 200 as a middle value there. This basically tells you how powerful your amplifier is, in the same way that a watt number on your guitar amp tells you how powerful that guitar amp is. This is just copied straight over from the schematic. So we've got RB1, which is the resistor of the base number 1, 220k, resistor of the base number 2, 68k. This is coherent with how I've written it on the schematic, so if you're not sure how these relate to the circuit, check that. And then we've got RC, which is the resistor on the collector. That's our pin 3 on the transistor. That's our 10 kilo ohm. And then we've got RE, which again is the resistor on the emitter, which is 3.3K or 3300. And then our capacitors here. This C3 we're going to come back to in a later video. This is a little trick you can do to get a little bit more out of the circuit, but I'll cover how this works when we've got more circuit to play with. And again here, this is just the check sheet so that I didn't forget our input and output filter cutoffs. So the cutoff frequency where it's going to filter from, and that's our 1.6, 1.5 range there. Now, you can't see it on the schematic, and we're going to go through the actual circuit in a minute and we'll be able to measure these things. But the voltage at the base is going to be 2.13 something, right? And you can work that out using the sum here, which again is on the schematic. So these values here are what we're going to be mathematically perfect, and we'll be able to compare what we actually get against these. And again, here's the gain that I've just worked out. So if I pull out the breadboard circuit here, again, in the little kit on Amazon, these breadboards are included, and I'll just go over how they work. Just pop this in here a little bit. So on these breadboards, you'll see on the bottom line here, there's a red and a blue indicator. They're not inherently linked to any positive or negative. They're just there for when you're using it so that you know what you're doing. These run lengthways across the breadboard, and this particular version has a break in the middle. So this section is separate from this section, and again this section is separate from that section, and they're also separate from each other. These holes in the middle, they run the opposite direction across, up and down the board here, and they're divided into lines here with the numbers, if you can see, so you can keep track of where your component leads are plugged into. There's also this trench in the middle. This is for if you're using op amps and things that don't want one side connected to the other. We're not going to worry too much about this. I've used it a little bit with the transistor just to separate things out, but this is just more of using different components. I will link these in the description. When it comes to powering your breadboards, I have a bench power supply which plugs into the wall. I appreciate not everyone has that. So you can use these little battery snaps that come with a lead on them. And all you would do is you take some pliers and you just snip off a little bit of the insulation and poke them into the relevant holes here. And then you can run the circuit on a 9-volt battery. So as you can see there, I just plug these in. I like to use the blue line as my ground and the red line as the power, the positive. It just helps me keep track of where I am when I'm building. If we have a look at what's going on here, I've tried to lay it out similar to how the schematic looks. I think this is actually 90 degrees to how the schematic is drawn. So I'll pull that round, there you go. So if we have a look at what's going on here, I'll kind of point out the components and you can follow along on the schematic, but I'll do my best to make it easy to follow along just on the video. So this is our RPD1 on the schematic, and it's going from, it's kind of hard to see on here, but it's going from the ground, which is the blue side of our power, across to the first hole, pin, actually I can move this across here, pin A, so A7, and it's just kind of poked in. I'll just show you a resistor here so you can see how these work. When you get them, they'll be kind of straight, and you just bend the legs down. You're not going to break them or anything. Just bend the legs down into a staple shape, and then you just kind of push them with a bit of force, and they kind of slot into the little holes. So we've got RPD1 going from ground across to A, column A, row 7. And then on that same line, I'm just going to move these out of the way so we can see a bit better. On that same line, 7, on E7, we've got our C1 capacitor. And he's going from line 7 to line 10. And then I've got our yellow bit of wire. It's just a bit of wire. You can use any thin wire. I might link some in the description so that you can pick up some of that. I don't know if the kit comes with wires, but if it does, any color. Just something that you know where you are. So our yellow wire comes from line 10 all the way across here to line 20. So that's our guitar input. Later on, when we connect this circuit up, we'll put a line here on pin 7 out to our input. It'll go through this capacitor, through this line, and into the base of our transistor. I use a red line here for our power. He's going into line 15 here. It's covered up by the wire, but it's pin 15 here. And then we've got our 220k resistor here going from line 15 and joining line 20. And then again, I've got a black wire here for our ground. And just note that it's going into the blue side of this strip and the red one's going into the red side. And he's joining into pin 25 there. And then this is our 68k resistor going from line 25 up to line 20 and joining the base pin 2 of our transistor, the 220k, and our signal, which goes back out to our input. So that brings us to pin 2 of the transistor, the input, the base. And if we follow this through, we've got one leg going out to pin 19 and one leg going out to pin 21. So this one here is our 10k, and I've jumpered across on the same line over the trench on pin 15, and he's going from the power to line 19 to join our collector. And we're also going to take our output line from that same point, pin 19, over here somewhere to pin 30, just out the way. And then we're going to take our emitter on line 21. This is our 3.3k, and we're going to take him to ground. And I've just jumped this across from the other side the same way with that. On our yellow line here on pin 30, we're going to go to the input of our capacitor all the way across, or still on pin 30, across to our second 1 meg, which is going to ground, the blue side. And then again a third yellow line over here so that we can connect our output later on. So if we jump back to the schematic really quickly, just to refresh ourselves of some numbers here. Up at the top here, we should see at pin 2, we should see 2.1 and a bit volts. At pin 1, we should see 1.4 and a bit volts. And at pin 3, we should see 4.5 volts. So with that in mind, I'm going to jump back to the circuit here. And I'm going to just pull this across here for a second so I can get my multimeter underneath. And I'll link a cheap one of these in the description. You don't need an expensive one. I just use this one quite a lot, so I bought a fancy one. On here you see you've got this AC wave with a frequency. We don't want this yet. We want this one, which is our DC symbol. Whenever you see that symbol, you're working with DC. And we're working in volts, so I'm going to put it onto the volts. And we should see this come up. We've got volts DC, and we're in volts and decimal point and millivolts. So I like to just double check what my power is doing. So I'm going to come in with my black probe onto the ground and my red probe onto the power, and we should see 9 volts. Now it's worth just double checking that, because it will throw your math out if your battery is 8.9, 8.5, 9.1. You just need to use that number when you're doing your base biasing equation, the one where you take the resistor values and multiply it by your power. So now that we know that we're accurate with our input power, we can start having another little poke around. So generally speaking, with DC you're working between 0 and your input number, in our case that 9 volts. So you can kind of just park your black probe on the ground, on a black line, doesn't matter which one, and now you're just using the one to poke around and see what's going on. So if we go in here, it's kind of hard to see, but this point where this yellow line comes in, we can probe here and we can see a number. So we're getting 1.996 volts, and we needed, well, we wanted 2.13 volts, but in the real world you have things like the breadboard has resistance, which is taking voltage out. This wire has resistance, which is taking voltage out. These resistors aren't mathematically exact, which is skewing results because they're giving or taking resistance out, voltage out. And there's just, real world problems that just go on with electronics. So 1.9, 2.1, they're good enough. They're good enough for what we're dealing with. So again, moving across onto the pin 2 here, pin 1 here, we should see approximately 1.4. We're getting 1.3.5, but if you consider our 1.9, that's approximately the same as having 2.1 take 0.6. We're 1.9 take 0.6. That's pretty spot on. And then we can double check our collector, and we should see about 4.5. We've got 4.9, but again, if we've got 1.3 here, that means that a little bit more water is flowing through, which means we'll get a little bit more voltage at the top. 0.4 volts is fine. We're not going to cause any damage to anything with that little bit of variation. In terms of real world spec, this circuit is behaving perfectly. We can adjust our numbers. There's things like this chip might not be exactly 200 HFE. These resistors might be a little bit off. And we'll see this when I come back to our measured numbers a bit later on. But it's always good to do this once you've worked out where you should be. Have a look at where you are, and if you need to make any changes, you can now go back to the drawing board. Usually it'll be these two components that will have thrown off everything on this side, but occasionally you might want to change this one for more gain, or change this one if you can't get this, if you can't get the gain that you want. We can have a look at what these numbers mean now that we've seen the circuit working. So we're still using this part. Maybe in our circuit this was a little bit lower, meaning the flow that it had through it to the sink was a little bit higher, which meant that the overall amplification that we could get is a little bit lower as well. Maybe some of these values here weren't exactly on, which again meant that some of these values down here weren't exactly on. The math relationships all stay the same, and we'll see how these values here with this relationship can kind of skew the results. We'll come back to the gain when we look at the signal traces, but for now, generally speaking, if these line up, then your gains will probably be pretty spot on. So our remit was that we wanted our collector voltage mid-rail. That's a fancy way of saying whatever our power was divided by 2. So 9 volts divided by 2, 4.5. We wanted stable DC, which essentially means that our output voltage wasn't flying around, and we're not basing our design on whatever our specific transistor's HFE is, which I think is the best way to design these things, because if you wanted to build 1 or 2 or 3 variations, you can work out mathematically how much gain you're going to get, as opposed to leaving it down to which part you got and playing the what they call the silicon lottery. We wanted moderate gain, and the reason we wanted, just a sensible amount is because we don't want the transistor to clip itself. We want to control that later on in a separate video. The emitter bypass, we're going to leave this out for a later stage, but essentially what it does is it separates the AC, I'll just draw this out for you, separates the AC gain from the DC gain. At the moment in our design, these two things are combined, but this isn't a problem. It just means that the absolute maximum gain that we get is a little bit less than what it could be. We'll come back to this. If we look at our actual measured values, I went ahead and measured our resistors. Our 220k was actually a 220.8k. Our 68 was pretty on the money. That was 68.k. And then we have 3.28k for our 3.3 and 9.97 for our 10k, which when we do the exact same math as before, and we have a look up here, let me just pull this back up. When we have a look up here, these numbers, and when we run that with our numbers down the bottom here, we end up with our 4.9 and our 1.96 and our 1.35, all of which we saw on the circuit with these numbers over here. When we run the currents, which we worked out in the math was going to be 0.45 milliamps, we can see that we've got 0.41 milliamps. Now that's some drop, that's 4 milliamps less. But when you actually look at the gains here, 2.94, and up here 2.95, in decibels that's 9.39 and 9.36. So we're still getting basically the same output, even though our actual values were not exactly what they should be for the math. Right, so here we are looking at the oscilloscope. Now a little bit of explanation here. We've got the blue line is our input. We're looking at the actual circuit, and we are feeding the circuit a 100 millivolt signal, so that's 0.1 volts input at a frequency of 500 hertz. I picked these numbers based on rough outputs of a guitar pickup and a frequency that is somewhere in the mid-range of a guitar. No point using a massively high frequency here if a guitar couldn't produce it. The red line is the output of the circuit, looking at the actual output. And down the bottom, you can see, I'll make them a little bit bigger. You can see these numbers jumping around a little bit. If I pause it, you can see the numbers here on channel A. We've got our 100 millivolts input. And on our output, we've got our 282 millivolts output. As you can see, if you take 100 millivolts and times it by 2.9, which was our gain that we worked out earlier, you end up with, 280 millivolts in this case. But again, real world circuits, real world components, that's about right. That's approximately what we designed it for. We've got symmetric waveforms going on here. If we bring these rulers down, we can see that we've got 141 positive and 141 negative, which is, that's symmetrical. The same above 0 as below 0. And if we again do the same thing on our input, we can see that we are less than a millivolt out on our input, and we're again less than a millivolt out on our output. So if you were to put a guitar signal through this, you would have no clipping or distortion from the amplifier. You would just have more signal coming out, which would be about 10 dB louder than what went in. So really quickly jumping back to our schematic here, we can see that we wanted approximately 3 or 9.5 dB. We worked out later on that 3 was going to be more like 2.9, and that we wanted it to be symmetrical up the top here, and that we wanted to have enough force on the tap here to let this current flow, which would allow us to get the symmetrical waveform, and it would be outputted 3 times roughly as big as what we put in. And if we just jump back to the oscilloscope here, just to round that off, our unit 1 coming in is about a unit 2.8, 2.9 coming out, which is perfectly within our spec and proves that the math does work, and that sometimes you just have to adjust some of the math for your actual components. For our circuit, we just needed it to be within the ballpark of what we designed it for, because we're going to end up distorting this with diodes next week.